Hi, my name is Wijntjes, and this is my lab for a macroscopic view of DC and RC circuits. As an introduction, the purpose of this lab was to predict the behavior of circuits in series and parallel. I did this using the Ohm's law, conservation of charge, the loop rule, and the node rule. I then measured values for conventional current and potential difference using different multimeters. I also examined the behavior of ohmic and non-ohmic resistors and capacitors. The method of this lab was a Java circuit construction kit used to simulate a real circuit. The CCK allowed for modeling and observing different circuits. The results were that the application of physics principles allowed for the accurate prediction of different current readings and voltage readings before the simulation was run. A comparison between predicted and experimental values was conducted after each simulation was run. I used the CCK to record time and voltage values across a charging capacitor that then allowed for graphical modeling and the calculation of the RC, or time constant, of the circuit. My percent error for this was 0.583%, comparing my 6.035 second experimental value to the 6.00 second theoretical value. These were some of the physics principles highlighted: conservation of charge in a steady state, the conventional current I is constant, the loop rule, the sum of the voltage differences across the circuit elements must be zero, the node rule, the sum of the current into the node equals the sum of the current coming out of the node, and Ohm's law, V is equal to IR, or voltage is equal to current times resistance. Some of my initial calculations for one of the circuits featuring 47 ohm and a 100 ohm resistor was that the current was equal to 0.02 amps. I got this using Ohm's law. I then modeled that same circuit using a circuit construction kit and got that the current was the same as my theoretical value, or what I calculated before, and it was 0.02 amps. I then inserted an ammeter backward and got the same result. I then inserted a voltmeter into that same circuit and got that the current reading using an ammeter was 0.00 amps. This is because the voltmeter led to a disconnected or open circuit. The voltmeter read 3 volts due to the potential difference across A to B being 3 volts. I then measured the potential difference across different sets of elements and noticed that the potential difference dropped significantly over the resistors. It did not change over the wires. You can see here is where I measured the potential difference for each element. This made sense that the theoretical value was 0 and that the experimental value was also 0, because over a round trip the potential difference sum should equal to 0. This is my potential difference graph I got from modeling the potential difference drop across each element in the circuit. You can see here that the main drops occurred over the resistors. The potential difference drop for the 100 ohm resistor was the greatest. This is because this element had the greatest resistance. When I put an ammeter and 100 ohm resistor in parallel, the current reading on the ammeter increased from 0.02 amps to 0.06 amps. The 100 ohm resistor was in parallel with the ammeter instead of being in series with the 47 ohm resistor. Current flowed through the ammeter due to it acting as an ideal wire and being the path of least resistance. This led to the current in the system to be 0.063 amps, an increase from 0.02 amps originally. I then calculated the resistance for each of the different elements in the circuit. You can see here my main findings for the resistance across each of the main elements in the circuit. I then looked at when a 10 ohm light bulb, a 200 millifarad capacitor, and a 9 volt battery were initially connected in series. The battery lit up the bulb initially, and the battery charged the capacitor. When a 10 ohm light bulb was directly connected to the charged 200 millifarad capacitor with no battery, the bulb started out very bright from the end of the last simulation, and then continued to dim as the capacitor discharged. The current in the circuit decreased eventually to 0 as the capacitor discharged. I then looked at inserting a 10 ohm resistor and a 20 ohm resistor, and then the capacitor charging time and capacitor discharging time. Initially, a battery was placed in when the capacitor charged and then removed when it was discharged. I then looked at the time-dependent voltage across discharging a capacitor RC circuit. I observed a circuit containing a 9 volt battery, 200 millifarad capacitor, and a 30 ohm light bulb. I measured the voltage across the capacitor with a voltmeter over the course of 20 seconds. I used the voltage and time values in the equation ln delta V divided by delta V initial is equal to negative T divided by RC. A plot of the ln delta V divided by delta V initial versus T yielded a straight line with a slope negative 1 divided by RC. RC is a time constant of the circuit. It is the time the voltage difference drops to 1e of its original value. I then modeled these values. Over the course of 20 seconds, I looked at the time and different voltage readings while the capacitor was charging. My slope of the line was negative 0.1657. I then used my line of best fit that I got from my previous graph to find the RC to be 6.035 seconds for my experimental value. My theoretical value was 6 seconds. The percent error for these values was 0.5833%. This meant that my theoretical value and experimental value were very close in values. If I used an actual ammeter in real life instead of an ideal simulated ammeter, a real ammeter exhibits some resistance, causing the measured current to be lower than the current of the system without the ammeter. Increase in resistance decreases current because they are inversely proportional. If a real battery was used to charge a capacitor in real life, how quickly would our ideal monoprotective capacitor to reach field charge versus in real life would this actually happen? The CCK predicts the capacitor would charge fully almost immediately. In real life, batteries exhibit some resistance, slowing down the process of charging the capacitor. This could also be due to faulty equipment. Thank you.